calculus involving trig functions. We'll start off differentiating sinax and cosax and look at how we use the chain rule to differentiate compound functions involving sinax and cosax. Trig functions are quite different in shape to most functions, and the gradient functions don't follow the same rules as we used to. So we'll do this by drawing the graph of y equals sin x to start with in degrees, which we're very familiar with, or hopefully. We'll look at the first quadrant between 0 and 90 degrees and then use symmetry to give us the rest of the gradient function. So drawing that out looks like that. Now let's have a look at what happens to the gradient at different points on this curve. Well, if we draw out a scale for the gradient function here, draw out 0 to 90 on the x-axis and just make an approximation of what the gradient looks like on this vertical axis here. So start off at 0 and we can see that the gradient looks like this. So if we just plot that somewhere on this vertical axis, say there, we can then see that the gradient's less, isn't it? It's flattening out a bit here at about 30 degrees. And then if we look again at about 60 degrees, we can see it's flattening out a bit more, so it's getting less. And then when we get to 90 degrees, it's flattened out completely, so it's 0. We can see here what we've just said, that it drops more slowly between 0 and 30 than it does between 60 and 90. So we can see here that our values look about right in relation to each other. Okay, and that's what we end up with. So a bit of an approximation, but that's what we end up with. So our gradient function looks a bit like the cos graph, but without a scale on this gradient axis, the dy dx axis, we can't really see whether it is the cos graph. So let's estimate what the gradient is at x equals 0, and we can do that by drawing the tangent till it reaches 1 on the y-axis, so it's gone up by 1 and it's gone across, as we can see there, about 60 degrees. So the gradient at the point where the angle is 0 is 1/60th. Cos 0, as we know, is 1, so we can clearly see that 1/60th doesn't work, or does it? Can you think of a reason why maybe it might work? Okay, what about if we use radians? Well, if we rewrite this in radians, we get pi over 2, which is just over 1.5, isn't it? And if we raise 1 again, if we go up 1, we can actually show that this distance here on the x-axis is exactly 1. So it does work as long as we use radians. And in fact, the derivative of sin x is cos x. We must be careful to always use radians when we're doing calculus with trig. And that's our result. Okay, pause the presentation and have a go at this yourselves. Do exactly the same for y equals cos x. If you do it between minus pi over 2 and 2 pi, using sensible points, work out the value of the tangent at those points and see if you can sketch a graph in the same way as we've just done it, and then suggest an equation for that gradient function. Okay, this is what you should have got. Well, there's the y equals cos x graph. Your gradient graph should have looked a bit like that. And if we look closely at that graph, we can actually hopefully recognise that it's a reflection of the sine graph in the x-axis which from your knowledge of transformations should tell you that the equation is dy dx equals minus sin x. So we now know what the derivative of cosax is. So to summarise, with x in radians, y equals sin x gives us dy dx of cos x, and y equals cos x gives us dy dx of minus sin x. We've not exactly proved those results, but we have shown that they look about right. So what happens with compound trig functions? It's all very well being able to differentiate sin x and cos x. What about if we've got something like y equals sine 3x? Well, to differentiate something like this, we use the chain rule, and as always, with a lot of the chain rule, once you've done it a few times, you can see how to shortcut it quite quickly. So let's work through this. So we make the u the angle, so u is 3x, which now gives us y equals sine u. Well, if y equals sine x gives us a gradient, a dy dx of cos x, y equals sine u will give us a dy du of cos u, won't it? Differentiate the 3x and we get du dx equals 3. Differentiate the sine u and we get cos u, which is of course cos 3x when we substitute back the 3x. We then put these back in the chain rule. Dy dx is dy du, cos 3x, times du dx, which is 3 cos 3x. And looking at that, you can see the shortcut, can't you? It's the 3 from there, and then it goes to cos 3x. Where x is pi, that gives us 3 cos 3 pi, which is minus 3. Okay, see if you can do this one yourself. So have a think about it, think how you're going to do it. Have a go at this one yourself. Pause the presentation and then I'll work through it for you. Okay, so y equals, well, I'm going to write this. Cos squared x is actually cos x all squared, isn't it? And maybe writing it like that makes it a bit more obvious what's going on. I'm going to use the substitution u equals cos x, the inner function. So that's now going to give us dy du here. Well, we've got y equals u squared, so dy du is just 2u, which is 2 cos x. And then the du dx part over here, cos goes to, well, hopefully you can remember this, if not look it up, minus sine x. Put them together, chain rule, dy dx equals dy du times du dx, which equals, well, dy du is 2 cos x and du dx is minus sine x, so we'll put the sine x there and we'll stick the minus right at the front there. Job done. Okay, another one for you to have a try then. Be a bit careful with this one. It's not the same as the one we've just done. It's not sine x all squared, it's y equals sine x squared. Have a go yourselves, pause the presentation, and I'll show you how to do it in a minute. Okay, hopefully that was successful. We'll write it out again. This time, and hopefully you work this out for yourselves, we're going to use the substitution u equals x squared. That gives us y equals sine u. So dy du equals cos u, which is cos x squared. For our du dx bit, we've got du dx equals 2x. So again, chain rule. I will write it out again, although hopefully by now you don't really need me to anymore. So dy dx equals dy du times du dx. Well, dy du is cos x squared, and du dx is 2x, and we would normally write that with the 2x in front, wouldn't we? Okay, if you manage to get those two right, then obviously you've understood this and you'll now be fine for the lesson. If not, go back over it, make sure you understand it.